All right, so take another minute to finish up our daily quiz. Remember, today is going to be review for our first exam, which will be happening tomorrow or Thursday, depending on what time you guys have that planned out. Our goal today is going to be to go through as much content as we can. Some people like to ask, like, oh, all I have to know is what we review today, right? No, I didn't just spend all that time lecturing to then tell you, oh, just throw that all away and only pay attention to what we do today. I'm just simply going to try to cover as many different types of problems as I can in the time that we have today. Okay? Just about the exam, the format of the exam is that it is multiple choice. Okay, so it will be a Scantron exam. All that sort of, your Scantron will be provided for you. You don't have to bring it in. You just need to bring in a writing utensil, a number 2 pencil, and a calculator. Okay? People love to ask me how many questions are on the exam. I don't get it. I don't know what you do with that information, but whatever number you need to hear that's going to make you study more, it's that many. All right? It's timed out to take an average student about an hour to do it, but you have the full 2 hours at the testing center. Cool. All right, so this is going to be our first problem here, an equilibrium problem. So everybody take a second. You have a chemical equation that is unbalanced, right? And you're given information about the initial concentration of your reactants and then the final concentration of one of your reactants at equilibrium. And from there, we should be able to calculate the equilibrium constant for this reaction, as well as the concentration of one of our species, in this case, our product, sodium chloride, at equilibrium. All right, so everybody take a second. What's the first thing we're going to have to do? Balance this chemical equation, and then you're going to set up your equilibrium expression and then your ice table. All right, so I'm going to give you guys a few minutes head start here, and then I'll sort of quietly go in and start filling this stuff in here. All right, so you can check your balancing. I'm going to start to build my expression here for my equilibrium constant. And what am I going to remember? What am I going to chant to myself? Products over reactants. All right, I got my products over my reactants. My stoichiometric coefficients in my balanced chemical equation are exponents in my equilibrium expression. And then I left out this magnesium phosphate here from my equilibrium expression. Why is that? Because it's a solid, right? Only aqueous and gases will appear in your equilibrium expression. All right, so now I'm ready to start building my ice table. All right, so now I'm going to get to my change box here, all right? So for my first one, magnesium chloride, what's going to be the sign in my change box here, positive or negative? Negative, because it's a reactant, right? Reactants get consumed, they go down, so this will be negative, and it's going to be negative what? 3x, because of that stoichiometric coefficient of a 3 in my balanced chemical equation. Same thing here, I'll have negative 2x because of the 2, and it's a reactant. And then finally for my sodium chloride, is that going to be positive or negative? Positive, and that stoichiometric coefficient of 6, so plus 6x. And then for my equilibrium box, I'm going to sum the other two boxes up. So 3.16 minus 3x, 2.55 minus 2x, and then 0 plus 6x is just 6x. Okay, so now I can take my equilibrium expression and plug everything in. All right, and again, just to sort of color code so we can see here, my concentration of sodium chloride at equilibrium, that's just what's in my equilibrium box for sodium chloride. My concentration of magnesium chloride at equilibrium. That's what's in my equilibrium box for magnesium chloride. And then finally, my sodium phosphate equilibrium concentration is what's in that equilibrium box for sodium phosphate. So I'm just going to plug those in. Okay? Remember to use your parentheses so that you don't mess up your order of operations. Kc is equal to 6x all to the 6th power, right? Not just 6x to the 6. These are not the same. Divided by, in parentheses, 3.16 minus 3x cubed and 2.55 minus 2x squared. Okay. All right, so now I need to, if I got x, I can just plug it in and I'm all ready to go, right? Can just plug that into my calculator. So in order to get my value for x here, I need to read my problem carefully. And it tells me that the concentration of magnesium chloride at equilibrium is 0.56 molar. Right? So where on my ice table is the concentration of magnesium chloride at equilibrium? That's that green box there, the 3.16 minus 3x. So now I know that my 3.16 minus 3x is equal to 0.56? So then I can just do some simple algebra here in order to solve for x. Did it somewhere. Okay, and I get that x is equal to 0.86666 repeating. Just going to put a bunch of decimals on there. All right, and I'm done. No, right? Yeah, you got to the other side of the algebra. You got your value for x, but remember what the problem's actually asking you for here. In this case, I asked you for two different things. I asked you for the value of that equilibrium constant. So we're going to go back to our equilibrium expression here, right? Plug in that value of x now. I have this whole thing all set up. All I have to do is plug in that value of x. When you're punching it into your calculator, make sure to use your parentheses. All right, and in particular, it's really important that since you have these two terms on the bottom, in your denominator, you need to throw these in parentheses or it's going to mess up your order of operations. All right, so if for whatever reason you don't get the same value that I get here in a second, make sure to go back and look at your calculation and make sure that you have both of those in your denominator. And again, the easiest way to do that on your calculator is to throw everything in the bottom in parentheses. Okay, yeah, boom, boom. All right, so plugging that in. Let me just double check my work here. Yep. So 6x to the 6 divided by, in parentheses, 3x to the third, and 2x squared. Wonderful. Okay, so we get a big value for Kc, 168,797 and some change. Okay, I guess just to put this in order in which we solved it here. All right. Is this an equilibrium that favors the products or the reactants? The products, because K is a big number, right? Anytime that K is greater than 1, we say that that reaction favors our products. And would we say that this reaction strongly favors the products or weakly favors the products? Strongly, right? We kind of have, it's a relatively arbitrary, it's just a helpful thing to keep in mind, cutoff of 10 to the 3, so 1,000, right? Anything greater than 10 to the 3, we would say would strongly favor the products. And in particular, this is probably a little bit of a low end for this value of K. These precipitation reactions tend to have very, very large Ks, very strongly favor the reactants here. Okay? All right, so now I have another question here, which is what is the concentration of sodium chloride at equilibrium? How am I going to figure out what the concentration of sodium chloride is at equilibrium? Where am I going to look? My ice table, I'm going to look in that equilibrium row, and in particular, I'm talking about sodium chloride, so that would be this box right here, the orange box. All right, so in order to get the concentration of sodium chloride at equilibrium, I have to take 6 times that value for x that we got. All right, so again, we solve for x here, but we just got to pay attention to what the problem's asking us for. It's asking us for the concentration of sodium chloride at equilibrium. which is that 6x. So again, plugging in that value of x, multiply by 6. I get 5.2 with a lot of zeros, so we're just going to leave it at that. Okay, and 5.2, what else does that number need? Remember, we can go ahead and ignore sig figs with our ICE table here because the algebra is a little complicated, but what do I have to make sure to put on this number? Units, right? And so what are my units when we're talking about concentration? Molar. That big M, 5.2 molar is going to be my final solution of sodium chloride at equilibrium here. Right? I could have also asked you for the equilibrium value of the concentration of sodium phosphate, right? And then you would just look on your table to that equilibrium box for sodium phosphate, right? So now we need to just take 2.55 minus 2x. So you can get your equilibrium, once you get the value of x, the hard part's over. Right? You just need to look back to your ICE table and make sure you're answering what the problem's asking you for. Again, people get lost turning numbers into other numbers. They get X and they're like, oh my God, I'm done. Thank goodness. That was brutal, right? Just remember to go back and pay attention to what quantity the problem is actually asking you for. All right? Okay. So we're going to just stick with this same reaction here. Okay. Whoa. All right. So let's say we have this mixture here, and we're going to assume we're at equilibrium. All right. But then I'm going to add a whole bunch of sodium phosphate. All right, so I let this thing come to equilibrium. Everything's all nice and balanced. And then I'm going to go in there and I'm going to drop in a whole bunch of sodium phosphate. Is it still going to be at equilibrium? No, I'm just going to have thrown everything out of equilibrium, right? So the question is, does this shift the reaction towards the reactants or products? Right? We threw this thing out of balance. We threw this system out of equilibrium. This reaction is then going to proceed until it reaches equilibrium again. So which way is it going to go? Am I going to start making more product, or is it going to go the reverse direction and start making more reactant to account for this adjustment that we just made here? All right, this was this asynchronous lecture video on Le Chatelier's Principle that we want to watch, that we should have watched. So let's just review real quick. The easiest sort of way to do it here is to just think about our equilibrium expression. And we don't even have to kind of think of the complicated formula that we just laid out, but let's just remember that we got products over reactants. All right? Now, if this system is at equilibrium, then I punch those values in and I get my equilibrium constant. Right? If it's at anywhere other than equilibrium and I'm using this expression, what do we call it? We don't call it K anymore, we call it Q. All right, so now we're going to change things up here. So we're going to call it Q just to be good. And let's just think, if I'm increasing the amount of sodium phosphate, am I changing this number on the bottom or this number on the top? If I'm increasing my sodium phosphate, that's one of my reactants, right? So I'm increasing the amount of my reactant that I just had in there, okay? So that means this value right here is going to increase. What's that going to do to the overall value of Q? Is Q going to get to be smaller or bigger than our equilibrium value if I make that denominator there larger? Smaller, right? If the denominator is bigger, the number as a whole is smaller. And you can just kind of punch numbers in, right? Like 1 over 2 compared to 1 over 4. Which one's bigger? Okay? But yes, so this means that if I increase that bottom number there, then I have a Q that's less than my equilibrium constant K. And if Q is less than K, which way does this reaction shift? So this will shift towards the product side. right? You're adding a whole bunch more reactant. You're throwing this out of equilibrium. The system has to respond by converting that reactant into product so that everything gets balanced back out. Okay? If we had real numbers, we could just plug them in and get our value of Q, right? Chatelier's principle is sort of a qualitative understanding of that same concept, right? Throwing something out of equilibrium by either adding reactant or adding product, or you can go in there and take stuff away. I'll take away some of my reactant or take away one of my product. And you can always go back to your sort of equation for Q here and just think, which value are you altering? Are you increasing the denominator or increasing the numerator? What's that going to do to the overall value of Q? All right, so let's just do another one here. Instead of increasing my amount of sodium phosphate, I'm going to remove sodium chloride. And I want to know which direction that's going to shift this reaction. So everybody take a second. If I let this system come to equilibrium, but then I go in there and I remove some of that sodium chloride, how is that going to shift this reaction in order for it to reach equilibrium again? All right, is sodium chloride a product or a reactant? Which one of these two numbers is going to be changed here, the numerator or the denominator? The one on top or the one on the bottom? The one on top, right? Because I'm now changing my amount of reactant, but I'm actually or my amount of product, but I'm actually decreasing that number up top there. So what's that going to have on the value of Q? Is it going to get bigger or smaller? Smaller. So we're going to have the same situation here where Q is less than K. Right? So notice that if I add reactant or remove product, I see the same effect, right? It'll shift things. The system has to respond by making more product. And then if we do the exact opposite, we would see that Q would be greater than K, which means that it's got to shift in the reverse direction towards the reactant. Right? So that would be if I were to remove reactant or add product. Okay? I teach this concept in Chem 3A, and they don't really get as far as learning about Q, right? So I tell them to think about it as kind of like a teeter-totter here, all right? So at equilibrium, everything is nice and balanced on my little teeter-totter between my reactant side and my product side, all right? If I then have the effect of adding some reactant, what's that going to do to my teeter-totter? Which side is going to be on the floor? All right, if I add to this side over here, now all of a sudden, this side's on the ground, this side's up top, my system's out of equilibrium. How do I put this thing back at balance? Am I going to take stuff from this side and move it over here? Or am I going to do the reverse, take stuff from the product side and move it over here? All right, how do I get my teeter-totter back balanced? You have to take from your reactant side over to your product side, right? So if you add reactant, the system has to respond by shifting towards the product side. Okay? If you're a mathy person, it might help more to think about it in terms of that value of Q, that ratio, what number are you changing? If you're like, man, don't love math, you can think about it as a little teeter-totter, and your reaction needs to get balanced again. All right, whatever works. But this is this concept of Le Chatelier's principle. It's actually really important in chemistry. We take advantage of this all the time by tuning our reaction conditions to maybe make more product if a reaction wasn't all that favorable. You see this in organic chemistry a lot. And typically you have something really expensive that you're trying to convert into product. So what do is you take your cheap reactant and you put a crap ton in, and that helps shift everything towards the product side, right? So we take advantage of this principle all the time, tuning our reaction conditions to help us get more product or maybe to stop an unwanted reaction. All right, so the other thing, now we got to rewind. So this is a good sort of review of what we learned in chapter 16. We also talked about this 3.16 molar. What the heck does that mean, right? So everybody take a second and give me the definition of molarity. In terms of what over what, units-wise? It's not mass, no. So, big M, molarity, what over what? Moles over liters. So that's the first thing you want to just remember, that the units themselves, okay? So, big M, molarity, and this is again going to be the most common concentration that we use in this course, is moles over liters. Okay? And specifically moles of what? My solute, and liters of solution. Okay, so got to keep those units in mind here. They're how we're going to use this in our problem here. So for example, if I said, let's take our 3.16 molar solution of magnesium chloride, and I want to know how many liters contain 2.76 moles of MgCl2. All right, our definition of molarity is going to become a conversion factor, right? The trick for these problems, for all of these concentration problems, was how do you take that 3.16 big M and turn it into something that you can use in your math? All right, so everybody take a second, see if you can't solve this problem, and then we'll do it together. All right, so remember we got to take that 3.16. Those are my moles of my solute magnesium chloride. and that's going to go over 1 liter of solution. All right, so this is what we see in our problem. This is the term that we're going to use in our math. So now we're going to take our 2.76 moles of MgCl2, and we need to use our concentration. Am I going to use it as is? Can I just line it up like that? No, right? Why not? How do I know that that's wrong? Because my units, right? And I'm always very good, just like I know everybody is when they're taking their notes about writing out my units. No, but seriously, it is very, very helpful. A lot of people get lazy and they kind of just put the numbers on the page. That's a great way to understand that calculation for the next 15 seconds. And then you're going to look back on it in a week and be like, I have no idea what this page of numbers corresponds to, right? So be really good about writing out your units. It'll save you a mistake as well as just make your notes more useful to look back on. All right, so absolutely, I'm going to have to flip this thing upside down. 3.16 moles of MgCl2 on the bottom, my liters of solution up top. So just punch that into my calculator. I get 0.87341. All right, what are my units? Liters, right, because moles of magnesium have canceled out, so I'm left with those liters of solution here. And then how many sig figs should I report this value to? 3, all right? So my initial number of moles has 3. My concentration has 3. So absolutely, my final answer would be 0.873 liters. All right, so that was one of our units for concentration. Remember, concentration kind of a pain in that we got multiple units that we use. Different fields really like different sets of units. This one's the most popular in chemistry. The other one that you will see in chemistry as well is the little fancy M, little fancy cursive M. And this is the symbol that we use for what? Molality. It's got way too many L's in that name. Molality. Okay? So everybody take a second and see if you can't give me the definition of molality. Solvent, yes. That's the tricky part. All right, so yes, for molality, we have moles of solute, but the big difference is what's in the denominator here is not in units of volume, but in units of mass, kilograms, okay? And it's not the mass of the solution, but specifically the mass of the solvent. All right, so everybody take a second and calculate the molality of this solution here. I was very creative with my number choices. So I'm just going to use my definition of molality. my 4.65 moles of my solute, sodium chloride. Okay. I got to do my mass of solvent, so I guess I could do it the long way just to point out here. Right? But I need this value in kilograms, so I'm going to use the fact that 465 grams times the fact that there are 1,000 grams in 1 kilogram. All right, so that would be my unit conversion all set up so that my units work out well. My grams cancel out, and so I'm left with this value of 0.465 kilograms of solvent. All right, I'm going to punch that into my calculator. My calculator is going to tell me 10. What should be the units on that? That little fancy M, absolutely. For molal. All right, and then how many sig figs am I going to report this concentration to? This has 3. This has 3. So how do I report my 10 that my calculator gave me to 3 sig figs? 10.0. So 10.0 molal. That's my solution here. All right, and then let's just do another one real quick because we need to, again, make sure that we can take that value and use it in our math here. So what if I asked how many moles of NaCl are in our 10 molal solution? That contains 2.5 kilograms of water. Okay, and again, the trick, the thing that I want you to focus on first is taking that concentration, that 10.0 molal, and turn it into something that we can actually use in our math. Right, that 10.0 fancy M, how am I going to use that in my math? I'm going to split up my units, so it's going to become 10.0 moles of sodium chloride over my 1 kilogram of solvent, which is in this case that water. So then to set this up, I'm just going to do my 2.5 kilograms of solvent. Am I going to be able to use this concentration as is, or am I going to have to flip it? It's cool as it is, right? Kilograms are on the bottom. So that 10.0 goes on top. Punch that into my calculator. I get 25. And what are the units? Moles, and specifically, right, moles of my solute, my NaCl. And what about sig figs? I'm actually cool, right? Just 2 sig figs on that one because my 2.5 only had 2. So even though my concentration had 3, I'm going to go with whichever number is fewer. So I'm going to have my answer rounded to 2 sig figs. All right, so we talked about concentration in molarity, concentration in molality. All right, and then the big one that you will see outside of chemistry and mostly in the health field would be percent mass. So let's do one real quick. So most nail polish removers, well actually some of the weaker ones actually, you can get them pretty crazy high acetone content. But one common nail polish remover will be about 5% acetone by mass, okay? So what mass of my nail polish remover contains 14 grams of acetone? All right, and again, trick is, how are we going to use this 5% by mass in our math here? All right, so everybody take a second, see if you can't remember how to set this one up. Again, the first step is, how do we use that concentration in our math?
I found this on the web.
Okay. All right, so this percent mass, 5.0% mass. That's 5.0 grams of my solute acetone. Percent by mass will be over grams of solution. Okay? But because it is a percent, it took the mass of acetone divided by grams of solution and then multiplied it by 100, right? So that 5 is how many grams of acetone there are in 100 grams of solution. Okay, not just one like we've been using previously when we built these. So this is what I'm going to use in my math here. From here, I just set it up, my 14 grams of acetone. I'm going to have to divide by my concentration that I just built here, right? So that grams of acetone cancel. All right, so I'm going to need 280 grams of my solution if I need those 14 grams of acetone. All right, so just to remind you, this is one of these mass percents here where you take grams of solute divided by grams of solution, but they're all multiplied by this factor F. For percent mass, it's a percent, so F is 100. For parts per million and parts per billion, that factor of F is 1,000,000 for parts per million and 1,000,000,000 for parts per billion. That's where those terms come from, right? And then when you're going to take that and use it in your math, you need to put the grams of solute over that factor F grams of solution. So in the case of our percent mass, that's why we use that 100 grams of solution in our math. All right, cool. All right, and then the last concentration that we discussed was mole fraction. Okay, and since we're going to do a problem, well, let's do of solute here. Okay, give me the mole fraction of solute. What would be the definition there? Yeah, total moles, yep. So mole fraction of solute, all right, that's going to be moles of solute over the total number of moles of everything in our solution, which would be the moles solute, plus the other part. What's the other part? Solvent. Right? One of the other things that we learned at the very beginning, the very first thing that we learned were these definitions, solute, solvent, and solution. I've been kind of throwing them around. Hopefully we're all comfortable with them and understand what they mean at this point. All right? Cool. So now let's say we have a solution of sucrose, where the mole fraction of sucrose, right, we use that fancy X for mole fraction, equals 0.16. Let's say sucrose in water. If the vapor pressure of water is 0.0313 atm, what is the vapor pressure of our solution? All right, so this is now wading into this discussion of colligative properties here. Can anybody tell me what a colligative property is? Definitions here. Good to know before an exam. What the heck do I mean by colligative? All right, so these are properties that are independent of the identity of the solute, but depend only on the amount of solute that you have dissolved in a given solution, right? So it doesn't matter if we're talking about a solution of salt water or sugar water, right? These properties will only depend on the actual concentrations, not on the identity of that solute. And there are a few of them that we learned about here. Okay, we learned about vapor pressure. The vapor pressure of a solution is always less than that of a pure solvent. We talked about freezing point and boiling point. Freezing point is always decreased in a solution compared to the pure solvent, whereas boiling point's the opposite. It's always greater than that of a pure solvent. All right? So if we look here on our constants page, our handy-dandy constants page, we have a few formulas here. Let's ignore all this. Boom, up at the top, our colligative property formulas here. Which one are we going to use for this particular property, A, B, or C? This very first one that's talking about vapor pressure here. And so I can see that the vapor pressure of my solution is equal to the mole fraction of solvent times the vapor pressure of my solvent. All right, so given that, everybody take a second and see if you can't answer this question here. We're going to use the fact that the vapor pressure of our solution is equal to the mole fraction of solvent times the vapor pressure of our solvent. All right, so I got a fancy X here. I got a fancy X in my problem. I got a pressure of my solvent here and a pressure of my solvent in my problem. So 0.16 times my 0.0313. And I'm done? No, why not? What's the fancy X that's given in my problem here? Is that the mole fraction of the solvent? No, that is the mole fraction of my solute. But remember, if we have the 1, we can always find the other very easily by taking 1 minus, right? So just to be clear, my mole fraction of my solvent is equal to 1 minus the mole fraction of my solute. That's what I was given in my problem here. My sucrose is my solute, right? So I'm going to take 1 minus that to get my mole fraction of my solvent, and then multiply that by that 0.0313. All right, and I will get 0.0262992. What are my units? ATM, right? So whatever units for pressure you're given, mole fractions actually don't have any units associated with them. So there's no like canceling out or following units here. My ATM that I was given, that's going to be my units in my answer. All right, and then how many sig figs? Should have 2. All right, so my final answer, 0.026 ATM. Notice that the notice that the vapor pressure of my solution is less than that of my pure solvent, right? That's always going to be the case because that mole fraction, that fancy X, is always going to be a value between 0 and 1. All right. Okay, so now let's go back to our constants page here. We're going to use another one of our colligative property formulas here. We're going to use this delta TF here. All right, and we'll just do it on this page because we got all this constant information that we're going to want to use here. Okay. All right, so we're going to take 0.549 moles of benzoic acid, C6H5COOH, and we're going to dissolve it into 649 grams of benzene. We need to calculate the molality here. Why do we need the molality? Right, because if we look in our formulas for these colligative properties, this is really why molality is used, is to study the effect of temperature on solutions. And so in order to use our colligative property formula here, we're going to need our concentration in molality. Once we have that, we can answer what is the freezing temp of our solution. All right, so everybody take a second and calculate the molality of this solution that we just prepared here. Right, that's C6H5COOH. Might be scary, but remember these properties are independent of the identity. You don't have to know a dang thing about that thing in order to solve this problem, right? Actually, I lied. There is one thing that we got to know from this formula here, and that is this compound ionic or covalent? Covalent. Why covalent? Because carbon and oxygen and hydrogen are all nonmetals, right? And that's going to be important because that first factor, that first variable in my formula here, that I, corresponds to the Van Hoff factor, which is just 1 for our covalent compounds here. All right, so again, everybody take a second, calculate our molality, and then finally see if you can't finish it off by calculating the freezing temperature of this solution. All right, so my definition of molality is my moles of solute over kilograms of solvent. So I'm going to take my moles of my benzoic acid, my C6H5COOH, and divide it by that 0.649 kilograms of my solvent, benzene. Punch that into my calculator. I don't know where it went. Get 0.845916. Fancy M. How many sig figs are there in that number? 3. So I'm going to mark my third sig fig there with the bar. And I'm going to round it off before I go and do more math. No, remember, we're going to keep that number. We're going to keep it with the sig fig marked, but we don't want to round it off and then plug it into our calculator again. Never plug a rounded number into your calculator. All right? So now in order to get my delta T of my freezing, this is I, molality, times that Kf. We said in this problem, I is 1. And what was our argument there? Because it's covalent, right? For any compound that is covalent, I will always be 1. Because we have a covalent solute. My M is my molality that I just calculated. And where do I get that Kf from? From the table, right? So I'm going to go up here, and where on this table am I going to look? For benzene, right? That's my solvent. So I'm going to look for my solvent benzene. That's this first one here. I'm going to follow that over until I get my Kf value, my 5.12 degrees Celsius per molal. All right, so for this problem here, 5.12 degrees Celsius per molal. So then I can just plug everything in. 1 times that value that I got for my molality. Times that 5.12. All right, so plug that all in. I get 4.33109. Okay, what are my units? Degrees Celsius, right? Within my constant that I got, it was degrees Celsius per molal. So those molals cancel out. I'm left with degrees Celsius. And how many sig figs are there? 3. And then I'm done. This is my freezing temperature. No, this is the change in freezing temperature, right? So I got to go back to my table. I got to grab my freezing point of my solvent, benzene, 5.5 degrees Celsius. Okay, 5.5. This is my TF of my solvent, benzene. And then am I going to add or subtract that delta T? Subtract, right? Freezing points always go down. Freezing point depression. So minus my 4.33109. Keep my sig figs marked. All right, I'm going to, since it's a subtraction problem, and I'm going to follow my sig figs, I'm going to stack these up at the decimal. Where's the sig fig going to be in my answer? What do we call that column? The tenths column, the TH on the end. Yep, that first decimal point there. All right, so I'm going to punch that into my calculator as is. I get 1.1689, etc., etc. My delta TF. So degrees Celsius, this is my freezing temperature of my solution, which gets rounded to 1.2 degrees Celsius. There's my new freezing point for this solution that we just created. All right. So now let's just say that we had a solution of magnesium chloride. All right, and I was going to use this same formula here. Okay, let's just look at this Van Hoff. We're not going to do a full problem because I want to sort of switch to something else in our last few minutes. But if I'm going to do this here, how would I get that Van Hoff factor? What would I do? So, two things. I would go to my table, right? And hopefully I would have magnesium chloride. And then I could use the actual measured value for that Van Hoff factor. All right, that's going to give me the most accurate calculation that I can do is if I can find it on this table here and use that measured Van Hoff factor. But now let's say that I was given something like, I don't know, MgBr2. What should I use for the value of I? Okay. What does that value of I stand for? Why is it only 1 if we're talking about covalent compounds, but we got to use these other values if we're talking about ionic compounds? They're the number of particles that this thing will dissociate into, right? Magnesium bromide, when you take it and you dissolve it into water, it doesn't stay magnesium bromide. You have a magnesium ion floating around and 2 bromide ions floating around, right? So this thing right here will break up into magnesium, bromide, and bromide. Right? And so yes, if we have the value on the table, we can use that and be even more accurate. Otherwise, we would just get what we would expect based on the formula, which would be how many particles it dissociates into. Right? If we look on our table here, we have these expected values. Where do those come from? Those are just simply how many particles these would dissociate into, right? 1 magnesium and 2 chlorides. Somebody went in and they measured and they got even better. But notice that those measured values are always quite close to your predicted values. So worst case scenario, you don't have a measured value to go off of. You would just use your predicted value based on the formula of that ionic compound. Okay? All right. So the last thing I wanted to do is we're going to look at some structures. And we're going to rewind all the way back to the beginning here where we first discussed that very first day. We're going to look at a few structures and we're going to try to figure out what the strongest intermolecular forces they would have, right? Looking at these different types of bonds here. All right, so the strongest intermolecular forces in each of these molecules here. So in each of these 4 molecules, you're going to give me the strongest intermolecular force that are present. So I know that everybody did nothing but practice this over the holiday weekend, but let's take a second and review what our options are here. Like what the heck are we talking about when we're talking about intermolecular forces, right? So when we introduce these, we introduce them on a scale from the very weakest to the strongest ones that we see. So let's just start there. If we have our very weakest type of intermolecular force, does anybody remember what that one is? Dispersion. All right, what's a little bit better than dispersion forces? Dipole-dipole. All right, and then even stronger than that, a nice very polar solution would have hydrogen bonding. And the very strongest of them all, ion dipole. Strictly speaking, ions aren't considered polar because to be polar, you have to have a polarizable group of electrons. So strictly speaking, they're not. Practically, how do I think about ions? I think about ions as being superpolar, all right? That's about as polar as you could possibly get, is having an ion, having a naked charge like that. All right, so again, here are our options. And again, for each of these molecules, you're going to look and tell me what the strongest intermolecular force is. Every single one of these have dispersion forces, right? Those are present in all molecules. But what I'm asking for is what the strongest intermolecular force is for each of them. So everybody take a second and see if you can't label these four here with that strongest force. All right, so that very first one, what do we got? Dispersion. All right, the dead giveaway here is if it's only carbons and hydrogens, right? That is a quintessential non-polar molecule that contains only carbons and hydrogens. There's another sort of more special case, and those are these supersymmetric molecules. So for example, carbon dioxide. All right, there was that video posted under our very first lecture that sort of reviewed how to spot molecules that are polar versus non-polar molecules that if you need to remember from when you first talked about Lewis structures, you should go back and watch that review video. Okay, what about this one here, NH3? These are hydrogen bonding molecules, yep. All right, and what about my C double bonded to my oxygen? This thing here, this is actually formaldehyde. So this would be dipole-dipole. All right, but wait, I got this carbon, and why is there no hydrogen bonding here? Absolutely, right? So to remember, to be hydrogen bonding, you have to be one of three special bonds. These are the only ones that can hydrogen bond. Nitrogen and hydrogen, oxygen and hydrogen, and fluorine and hydrogen. All right, if you're one of those three, then you can hydrogen bond. And then this last one here, what's this one? So this is an ion dipole. How can I spy that it's ion dipole? Because I got this charge here, absolutely. And anytime you get a naked negative charge like that, or positive charge, those are the strongest, the superpolar, right? The strongest of all our intermolecular forces. So this one would be ion dipole. Cool.